We're now going to look at the 18th century, primarily Charles Darwin, but also a few individuals before him. We're going to start out with Erasmus Darwin, who was Charles Darwin's grandfather. Erasmus Darwin wrote a book called Zoonomia, and in this book, he actually very nicely continues to represent the mechanistic point of view. You'll recall that I talked about mechanism when I mentioned Descartes, mechanism being contrasted with Aristotle's vitalism, mechanism being the nurture side of the nature-nurture controversy, according to which behavior is more a function of physical laws and experiences rather than some inborn entity like a soul. He also continues the Aristotelian point of view of continuity, evolutionary continuity between human and non-human organisms. We'll see that Charles Darwin did the same, especially in one of his later publications. And there's an interesting developmental link that often goes unnoticed in Zoonomia, and that is he mentions, almost in passing, how prenatal movements actually affect postnatal walking. So in a way, this predates the contributions of a guy named Preyer. Preyer is often thought of as the father of behavioral embryology, and rightly so. I mean, he had huge contributions in that area. But in a way, it was Erasmus Darwin who came before him that actually was talking about the effects of prenatal behavior on postnatal behavior. In this case, how prenatal movements affect postnatal walking. Okay, next person. I'm not going to say all of those names, but they're all of his names. We'll just call him Lamarck. Lamarck is known primarily for the theory of the inheritance of acquired characteristics. What was behind this theory is that the use or disuse of various localized parts of your body cause changes to those parts. And, here's the big controversial part, those changes could be transmitted to the next generation. I mean, yeah, of course, the use and disuse of parts will cause changes or can cause changes depending on what those parts are. If you are lifting weights, you'll have more muscles in your arms and chest than a person who isn't. The question is, are you going to pass those on to the next generation? That's where the controversy occurs. And generally speaking, no, you won't. Herbert Spencer was a British philosopher, and he wrote a book called Principles of Psychology. It was the very first book that had the word psychology as part of the title. And in this, he continues the Aristotelian view of evolutionary continuity. But he also wrote a book called Social Statics a few years before Principles of Psychology. And in Social Statics, he coins the term survival of the fittest. Now, I mentioned it in a previous segment that Darwin was well aware of that. He adopted the term in his own theory of evolution, but he gave Herbert Spencer full credit. Herbert Spencer used this in a very negative way, though. Now, Britain was a greatly stratified society. There's this upper class, middle class, lower class. The upperclassmen wanted nothing to do with the lower classes. And, of course, Spencer was an upperclassman. And so he was talking about survival of the fittest in relationship to poverty and starvation. Let them work as natural cleansing agents to get rid of the unfit. And who are the unfit? The lower classes. Basically, it was something like this.
Children, I want each of you to bring in one can of food, and later the mayor of South Park will divide it up amongst Kenny's family and other poor people.
I'm not bringing in food for poor people. Screw them.
Don't you want to help those who are less fortunate?
Hey, you guys, do you hear something? I think I hear the flower children calling.
This is the one time of year you're supposed to care about people who can't eat.
Isn't it enough that I pay taxes? What about the poorhouses that I pay for?
Many would rather die than go to those places.
Well, then perhaps they should, and decrease the surplus population.
Okay, well, that's Herbert Spencer. Let's move on and talk about Charles Darwin. And the rest of this segment will involve Charles Darwin. So there's young Charles Darwin. Now we have the invention of the camera. Okay, so there's middle-aged Charles Darwin, and here is elderly Charles Darwin. So, of course, Charles Darwin, best known for his book The Origin of Species, that went through several editions with some changes in each edition based upon suggestions from colleagues and some of the controversies that the earlier editions had generated. Darwin was a naturalist on the HMS Beagle, and that went around South America and ultimately from Ecuador out to the Galapagos Islands. He was making a lot of observations everywhere, but of course, most of his observations come from the various stops in the Galapagos Islands. So there they are off the coast of South America. And different islands, different types of ecology on each of the islands. And because of the varying ecologies on the various islands, those differences pose different challenges for the various species that inhabit each of the islands, especially a group of birds called Darwin's finches. There's a biological research station there to this day. It's actually named after Charles Darwin. And so those are the various stops that Darwin made along the way. Got to most of the islands. And then he returned to England and went back to his house in a village called Down. And in fact, his house is known as Down House. It's actually a museum that you can go into now. The back area of Down House. And that's the library where he actually wrote The Origin of Species. So, this is his theory of evolution by means of natural selection. You'll also recall that it goes back to the writings of Empedocles. So let's look at this theory. First of all, there is organismic variability. Yes, there is, no question. Members of the same species are different from one another. We're all different from one another. The environment is always in a state of flux. It's always fluctuating. There are periods where more resources are available, other periods where fewer resources are available. Temperatures are always changing. It's always in a state of flux. So there's going to be competition for varying resources in these changing environments. And some animals will be able to garner more resources than others. They will adapt to these changes more successfully than other individuals of the same species. Why? Because organisms are variable. And that's going to result in reproductive success, or biological fitness, or evolutionary fitness. It goes by various names. Basically, if you survive to reproduce, this is Darwin speaking now, because this part of the theory has undergone some modification over the years, and we'll look at that in a later segment. But if you survive to reproduce and get your genes across to the next generation, you are now deemed evolutionarily or biologically fit. You have become successful. And ultimately, that might lead to speciation. I mean, remember the title of the book is The Origin of Species. So that might lead, not necessarily lead, but might lead to speciation. And by operational definition, you have created a new species, or evolution has, natural selection has, once you are a reproductively isolated unit, meaning that you can successfully reproduce among your own kind, but not with other kinds. Here's how Darwin put it.
Owing to this struggle for life, any variation, however slight, and from whatever cause proceeding, if it be in any degree profitable to an individual of any species, in its infinitely complex relations to other organic beings and to external nature, will tend to the preservation of that individual and will generally be inherited by its offspring. The offspring also will thus have a better chance of surviving, for, of the many individuals of any species which are periodically born, but a small number can survive. I have called this principle, by which each slight variation, if useful, is preserved, by the term of natural selection.
So that basically describes what he meant by natural selection, which is in essence what I just mentioned on the previous screen. This is really the best statement I've ever seen. And, if you understand this, then you understand natural selection. So before you even proceed, you might want to pause and reread this and make certain that you understand it. Darwin never said that we evolved from chimpanzees or modern apes. This is something that people say he said and then proceed to criticize him, which is dumb. You can't criticize somebody for something they never said. What he did say is that we have a common ancestor. Here's what he said.
I have found it difficult, when looking at any two species, to avoid picturing to myself forms directly intermediate between them. But this is a wholly false view. We should always look for forms intermediate between each species, and a common but unknown progenitor. And the progenitor would generally have differed in some respects from all its modified descendants.
That's right, a common but unknown progenitor. So how does speciation actually occur? Okay, let's look at that, because remember, the book is called The Origin of Species. Darwin, in this book, gave us a concept called correlated variation. Okay, here's what he meant by that.
Correlated variation is an important subject for us, for when one part is modified through continued selection, either by man or under nature, other parts of the organism will be unavoidably modified. From this correlation, it apparently follows that with our domesticated animals and plants, varieties rarely or never differ from one another by a single character alone.
Now, he used domesticated animals and plants as sort of a model, a microcosm, so to speak, for what goes on in the wild forms, because with domesticated varieties, you can actually see changes happen rather rapidly over successive generations when you select for various characteristics. That's artificial selection, sort of a model for natural selection. So that's why he just happens to mention domestication here, but everything he's talking about applies to natural selection as well. So,
other parts of the organism will be unavoidably modified. Varieties rarely or never differ from one another by a single character alone.
So whether there's a particular trait in the wild form that has been favored by natural selection, therefore that trait will be represented more and more and more in subsequent generations, or in the domestic form, the trait that's been artificially selected by humans, that's not the only trait that is going to change. Other traits will change as well, even though those other traits may not play much of a role in adaptation, going back to what would happen in natural selection. You're not just going to see a change in the one trait that might be important for adaptation. Other things will change as well. Now think about that. If that's going to happen, you can ultimately, over generations, many generations, end up with an organism that is so different from the original form that it is now, guess what, reproductively isolated, meaning you have now created a new species, or rather, natural selection has done so. Other parts are going to change as well. The modern genetic term for correlated variation is pleiotropy. So you may have your adaptive trait right there, the one that natural selection is acting on. And of course, every trait has an underlying genetic basis. The genes don't code for that trait, they code for proteins, but everything does have to have a genetic basis to it. And in reality, any given trait is what we call polygenic, meaning that there are many genes that provide a basis for any particular trait, or at least there can be. But with pleiotropy, we'll just look at one gene here. So yeah, the gene that provides a basis for that trait, the adaptive one, it's going to provide a basis for other traits as well. And so if this one trait stands a chance of being more greatly represented in other generations, then so are these other traits, even though they may play no role in adaptation whatsoever. So that, you'll end up with an organism that is quite different from the original progenitor. Let's look at thermoregulation as an example. There are many physiological and behavioral mechanisms that different species have to more efficiently thermoregulate because the temperature is changing. It changes from season to season. It changes from year to year. And so you'll see that the traits that are adaptive in terms of thermoregulation are going to help those individuals that successfully thermoregulate survive to reproduce, and those traits should be more greatly represented in subsequent generations. But other traits will be as well because of the pleiotropic effect of genes, or again what Darwin called correlated variation. Here's an example.
For example, suppose there's a herd of elephants in Russia and it's getting cold because there's going to be an ice age. Then there's natural variation among those elephants and how much hair they have. The ones that are hairier on average, not every single time, leave more offspring because they do better as the cold advances. And 100 generations down the line, you get woolly mammoths.
But other traits will change along with it. The tusks might change, and other characteristics as well. Maybe the size of the animal might change. Maybe the color of the fur might change. It could be lots of different things that are changing when the most important thing in terms of adaptation happens to be successful thermoregulatory mechanisms. So, geological time is a long time. And so when we're talking about natural selection and the action of the pleiotropic effects of genes, we're talking about hundreds of thousands of years in terms of geological time before you're going to be seeing these changes take place. And that's why Darwin used domestication as a model for natural selection, because sometimes you can see changes occur in just a couple generations. And we'll look at that much later in the course when we have a segment on domestication. So again, the origin of species, speciation. So let's look at crickets, for example, and the song patterns that the males sing. In other words, the chirps, the cricket chirps. So we start with one species of cricket, and there might be 3 varieties or morphs of that one species, but they're all the same species, and they're occurring within the same local population. But you can notice from these oscilloscope displays, basically you're looking at amplitude across time, that morph 1 has one song pattern, morph 2 has another one, and morph 3 has a different one. So suppose there are females within this population, and there are some females that only like to mate with the guys that are singing the pattern found in morph 1. Others like to mate with morph 2 guys, and others with morph 3. So you can start to see where within this population you might have subpopulations start to emerge with very little cross-mating among those subpopulations. And ultimately, way down the line in geological time, guess what? You could end up with different species of crickets because they've become reproductively isolated from one another. Here's another example. This comes from Drosophila, or fruit flies, the common name. So this was an experiment actually done in a laboratory where we have an initial sample of fruit flies, and they're fed on different diets, and they're maintained that way over generations. So some are always getting diet A, and others are always getting diet B, generation after generation. And then several generations later, you start to see some changes in these animals, some color changes as portrayed in these drawings. And then the females of the first generation, of the diet A generation, if given a choice between mating with the individuals of diet A versus diet B, happen to prefer the diet A individuals. And the females of diet B happen to prefer the diet B individuals. So you can see you have what's called assortative mating. And ultimately, this could lead to speciation, even though they were originated from this one initial sample of fruit flies. And so this is basically how speciation can occur, how the origin of species happens. Okay, here's another example. Alligators. Reptiles in general, but we'll start out by looking at alligators. So alligators lay their eggs in dirt, basically. They dig these holes and they'll lay their eggs and they'll cover them up. And then after that, mother alligator wanders off, has nothing more to do with those eggs. So they're basically incubated by the temperature of the soil in which they are buried. Now, it turns out in reptiles, sex is temperature dependent. The sex of the individual is determined by the incubation temperature of the eggs. So you can see where it's important that alligator moms choose the right temperature in terms of where they're burying their eggs. If they choose to bury their eggs in something that's too warm or too cold, then there are going to be some important issues and ramifications for the continued existence of the alligator species. Because here's the situation. If the eggs are laid in temperatures less than 86 degrees Fahrenheit, they will all develop into females. If they're laid in temperatures warmer than 93 degrees Fahrenheit, they will all develop into males. So if females were, for whatever reason, choosing nothing but very cold temperatures, less than 86, not that less than 86 is necessarily cold, or warmer than 93, you'll end up with all of the same sex. And, you know, we're dealing with a species where reproduction is bisexual reproduction. You could end up with them going extinct really, really quickly. So it behooves them to choose temperatures somewhere within the range of 86 to 93 degrees, where you'll end up with some females and some males, and you'll have the continuance of the species. Look at leopard geckos, another interesting situation. People buy these guys as pets. They're rather colorful.
The female goes away to lay her eggs. She has chosen a place where the temperature is about 31 degrees. As her body is the same temperature as her environment, she can't heat her eggs by sitting on them as warm-blooded birds do, so they're exactly the same temperature as the rocks beneath. After a couple of months, both eggs begin to hatch. The first to emerge is a male. And the second will be too. It's the temperature which has determined that. If it had been a few degrees lower, both eggs would have developed into females.
Same situation. The temperature that was mentioned there, by the way, was in centigrades. So an experiment was done to look at this a little bit more carefully, where some eggs were incubated at 79 degrees Fahrenheit. They just kept it constant, 79 degrees. And they all developed into females. Other eggs were incubated at 90 degrees Fahrenheit, and they developed into males, mostly. But some did develop into females. The experimenters referred to them as hot females. Hot in relationship to the 90-degree temperature, by the way. Don't read too much into that. So what are these hot females like? Well, for one thing, they were much more male-like in their behavior, especially in terms of aggression towards one another. The non-hot females, the females that hatch at the 79 degrees, are typically much less aggressive than males, or these hot females for that matter. Also, those hot females were infertile. It turns out that that was the case as well. So again, you can see where those eggs need to be incubated, in the wild of course, in the proper temperature range. Otherwise, you can run into problems for the continuance of the species as a whole. So, yeah, can you think of any reptiles that might have been affected adversely by this kind of temperature dependency? How about this? dinosaurs are extinct. Well, lots of theories as to why that's the case, but one possibility is that their temperatures changed, it got colder, and then suddenly, within a couple generations, only one sex was being produced, nothing but females, and that would cause them to get wiped out pretty quickly, at least in localized areas. Again, many other explanations for the extinction of dinosaurs, but that is one possibility since they were reptiles.
Why did all the dinosaurs die out?
Because you touch yourself at night.
Well, that's an alternative hypothesis. I don't think that one holds much water. If only things were that simple. The geneticist R.A. Fisher had a theory of called frequency-dependent selection. Frequency-dependent selection. Basically, what the theory states is that we're dealing with a situation where the relative occurrence of one phenotype is dependent on the relative occurrence of the other phenotype within the same population. So as he puts it, it's an evolutionary process where the fitness of a phenotype is dependent on the relative frequency of the phenotypes in the population. In other words, I'll simplify it even more, the number of males depends on the number of females in a local population of individuals of a particular species. The number of males depends on the number of females. And again, think about that in relationship to the temperature situation with reptiles. If you have nothing but females, you're in big trouble. If you have nothing but males, you're in big trouble in terms of the continuance of that species. Anyway, so yeah, unless you have that, you're going to have very skewed distribution of the sexes. You'll have too many males relative to females or too many females relative to males. Generally, that's not a very good scenario. So here's an experiment that was done to look at this theory. Atlantic silversides, a type of fish, they are temperature dependent as well. Like reptiles, it turns out this particular species, the determination of the sex depends on the temperature of the water in which the eggs are laid. Okay, so they took some individuals and put them in cooler water, and other individuals were in warmer water. Okay, so males and females in cooler water, other males and females in warmer water. 6 years later, this is a long-term experiment, they found that there were more males hatching out in the cooler water and more females hatching out in the warmer water. So there were skewed distributions in terms of the number of males and females in each of these tanks. Well, fortunately, they carried this out for another 1 to 4 generations and found that somehow the number of males and females started to even out. There were about as many males and females in the cold water as there were in the warm water. So it sort of went right back to where things were in the beginning with about the same number of males and females. Something happened that actually caused a reversal of the skewed distribution. Another experiment with butterflies. Okay, so here's some butterflies that are found on these 2 islands in the Samoa Islands. And we have some female butterflies, we have some male butterflies. So actually, I'm sorry, this is not an experiment. This actually happened on these islands. So it turns out that there was a maternally inherited bacteria that was devastating. It selectively killed developing male embryos, but left the females alone. So what was going on in 2001 was an incredible skewedness of the distribution of females relative to males. The males were being killed out by this bacteria. And so there were about 100 females to every 1 male. I mean, that's a horrible situation. But guess what? 10 generations later, in 2005, it evened out. They were back to normal once again. The bacteria were still there, but apparently what was going on was that they became less efficient in killing off the male embryos, and so more males were survived. They were somehow developing some kind of an immunity to this devastating bacteria.
There's one thing the history of evolution has taught us. It's that life will not be contained. Life breaks free, it expands to new territories, and it crashes through barriers painfully, maybe even dangerously, but, well, there it is. There it is.
You're implying that a group composed entirely of female animals will breed?
No, I'm simply saying that life finds a way.
A good way of summarizing Fisher's theory of frequency-dependent selection. Okay, Darwin wrote another book, Sexual Selection. Actually wrote a lot of books. I'm only going to mention this one and then one other after it. Sexual selection is something that he writes about in the book called The Descent of Man and Selection in Relation to Sex. And according to his view of sexual selection, which is a special case of natural selection, it's something to account for extreme cases of sexual dimorphism. Here we're looking at the same species. It's called the painted bunting. The very colorful male is on the top. The less colorful female rather, is on the bottom. So one sex is extremely different in appearance than the other sex of the same species. That's what we call sexual dimorphism. And he says, according to Darwin, what Darwin says is you'll see these extreme forms of sexual dimorphism occur if the males, because it usually is the males that are the more colorful. There's a couple exceptions to that species-wise, but I'll just talk about the males. If the males have some form of reproductive success, if a trait confers reproductive success onto the male, meaning the females like that trait and choose to mate with the males that have more of that trait, then that trait has been sexually selected. It can have no other role in terms of adaptation. Having that particular trait, being more colorful, cannot also help you get more food, cannot also help you escape from predators more or prey on whatever it is you prey on more. It can only have a sexual advantage. If it has a sexual advantage and any other advantage, then it just kind of falls back to natural selection. It's not sexual selection. It's sexually selected only if it confers a reproductive advantage onto the possessor of that trait, which again, more often than not, is going to be the male. So that is one of many things that he writes about in The Descent of Man. And we'll be looking at sexual selection later in the course in a separate segment. The other book that I wanted to mention by Darwin involves body postures and what we see here, facial expression in not only humans, but also non-human organisms. Postures, facial expressions, like that, like that, like that. Looks worried about something. Well, who knows what's really going on there. Anyway, the book is called Expression of the Emotions in Man and Animals. And in this book, he focuses primarily on continuity between human and non-human organisms. So again, it's the whole Aristotelian view of evolutionary continuity. You'll recall that Darwin's grandfather, Erasmus Darwin, also carried on that view, as did Herbert Spencer, as did many people that I haven't even mentioned. So continuity between human and non-human organisms, in this case, in terms of how we express our emotions, in terms of postures, facial expressions, things like that. And so these drawings and these photographs come from Darwin's book, showing how different postures reflect different emotions in non-human organisms, and of course facial expressions as well in human and non-human organisms. So these also come from his book. This is the crested macaque, and it's doing what he called chuckling when it's petted by a human.
The 6 basic facial expressions he identified were those of happiness, sadness, disgust, surprise, anger, and fear.
Happy, sad, disgust, surprise, anger, and fear. These are things that humans exhibit in facial expressions. What are the universal primate emotions?
Fear, disgust, happiness, surprise, and anger.
So, non-human primates don't have sadness. That's not been identified in non-human primates. But they share these other facial expressions with us. And interestingly, you can also look at brain scans of human and non-human primates.
Brain scans reveal that monkey and human brains display an identical pattern of electrical activity when experiencing fear.
And that would be primarily in the amygdala, which processes fear in human and non-human primates, and mammals in general, for that matter. So again, looking at his book, we have aggression. Here's a body posture, a submissive posture in a dog. And facial expressions, he actually worked with a physician who got some human corpses to dissect the face. Darwin wanted to know what muscles were in the human face, and then how they moved, how each individual muscle moved to produce the various facial expressions. So to figure that out, he hired actors and actresses to adopt various kinds of emotional expressions. And then he would feel the muscles in their face and try to map that onto the muscles of the dissected face of the corpses. And so both of these figures are found in Darwin's book. It's a classic book. Anyone who studies nonverbal communication today refers back to Darwin's book. And here's an example of nonverbal communication, but now we're going to look at it in birds. A rather interesting example involving body postures in the context of courtship. So there's a male courtship. You can hear the song and you can see the body posture. Here is the body posture of a receptive female that's been sung to by a male and she wants to mate with him. It's that posturing right there. But cowbirds are interesting. They sing many different types of songs to females. But typically, a female is not going to become receptive until he starts singing the same segment over and over again. Well, here's where the nonverbal communication comes in. She quickly signals to him which segment she likes. And then he will continue to repeat that segment, leaving the other ones out, and then hopefully she will become receptive to him after he goes through all that hard work of repeating the same thing over and over again. So let's look at that. Here's a female. There's a male singing all these different songs. Now, watch the female. These are still photos, obviously. Notice he was repeating the same thing over and over again, and that's what he'll do when she does this really fast wing stroke. It took frame-by-frame film analysis to even see the wing stroke. It happened so fast, but he's paying a lot of attention to what she's doing in terms of her nonverbal communicative behaviors while he's singing to her. He's looking for that wing stroke. So here he's singing. The song starts over on the left. Really fast wing stroke in the middle. You can see the male is intensively looking at her, looking for that wing stroke. a bunch of different songs before the wing stroke. Okay, now watch what happens. There comes the wing stroke. So he repeats the segment right before the female's wing stroke. And hopefully she's happy now and they will reproduce. So we have nonverbal behavior on the part of the female that basically is affecting greatly the vocal behavior of the male. Okay, so that's Charles Darwin, his contributions, at least some of his contributions. He had many others, and some of the people that came before him.